Time to do some problems involving trigonometric substitution, a wonderful way to combine two of our passions, trigonometry and substituting. Trigonometry is a fantastic tool because there's so many wonderful identities. It really lets us play around and have lots of opportunities to rewrite things in a simpler way. Similarly, substitution, a wonderful idea that says, hey, by changing what we call things, things become simpler. Sounds beautiful. Now, it does take practice because what we're doing is transforming our problems from one setting to another setting. And as with anything that takes practice, it's important that we do practice. The more that we do, the more second nature it becomes. The more that we see the right patterns and, in this situation we should do this, and in that situation we should do that. So make sure you're doing as much practice as you can. If you're following along with the video, make use of the pause button. See a problem that you like? Pause it. Try it yourself first. What's the right substitution? How do we rewrite things to get to the point where we see what the right substitution is? If you ever need help, I'm here. Just unpause me and we'll figure it out together. So keep going because I know that the more you do, the better you're going to become. And we want you to be fantastic. We want you to be great. Well, let's begin. Our very first problem. Find the integral from 0 to root 8 of square root y to the 4th plus y squared dy. All right, a nice, easy warm-up problem for us to begin. Now, as you look at this, you might say, hey, y to the 4th and y squared on the inside, they have something in common. They have a y squared. So, seems like a reasonable thing to do is to factor out what they have in common. So let's see where that takes us. So that's the square root of y squared times y squared plus 1 dy. Let me say, square root of y squared, we can simplify that. Square root of y squared is y. And note here that we do pause for a second and say, okay, well, y is going from 0 to root 8, so y is always greater than or equal to 0. We don't need to worry about the possibility that we need an absolute value. So we're okay. We're all right. So now we have y square root of y squared plus 1. Great. Wonderful. Well, where do we go from here? Well, it depends, right? So one of the things that often happens is once we get a shiny new tool, we're like, ooh, this is such a wonderful tool. And we're going to be like, you get a trig substitution, you get a trig substitution, you get a trig substitution. All our problems get trig substitution. But I think that's a dangerous thing to do. We shouldn't be overexcited and say, okay, everything's a trig substitution. We should always remember, hey, some of the first tools we learned are the best tools. So don't always jump to trig substitution. For instance, here, is there something else that can be done? And I think there is. So if you take a look, say, for example, on the inside, you see y squared plus 1. You say, the derivative of y squared plus 1, you can do that in our head, would be like a 2y dy. There's a y dy right there. Just normal substitution could actually help us here. So what would happen? Well, if we did let u equal y squared plus 1, then du, 2y dy. Now you might say, well, Steve, there's no 2. Well, okay, we can fix that. That's not so bad. Put a 2. But wait, if there's a 2 there, I'll also put in a half. So they see the half and the 2 balance out. So what happens? Well, this becomes the following. This would be, the integral from, we'll do the balance in a second. There's the half. The 2y dy is du, square root of y squared plus 1, square root of u, but we would write that as u to the half. Let's do the bounds. We originally went from 0 to root 8. So when we plugged in 0, that means y equals 0. So 0 squared plus 1 makes 1. Root 8 squared plus 1 8 plus 1 is 9. 1 to 9. Great numbers. All right, well, we can integrate here. So that would be 1/2 u to the power of 3/2 times by the reciprocal of 3/2, 2/3. Ah, nice. The 2's cancel. Cool. So what do we end up with here? And, well, don't forget 1 to 9. 1/3, 9 to the power of 3/2, minus 1 to the power of 3/2. Now, if you take 9 to the 3/2, you can do a couple different things. You can think of it as saying, take the square root of 9 and then cube it. So that would be 3 times 3 times 3, which is 27. Another thing you could do is say, oh, that's like 9 times square root of 9, which is 9 times 3, which is 27. And of course, the really hard thing you can do is say, well, 9 cubed is 729, and then the square root of 729 is 27. That's the hard thing, though. We won't do that. So, but the point is that's 27. 1 to 3/2 is easy. That's 1. So we end up with 26/3. Now, you might say, what? I thought we were doing trig sub today. Well, I think one of the important things to know, or at least to remember, is don't get too caught up. You know, in the future, you're going to see lots of problems without context. Right now, we're doing problems where we're like, oh, our theme for our session is this technique. So it's like, okay, you just get ingrained into that technique. But in the future, you might just say, well, here's a problem. And you could say, well, all right, great, what technique? And then the response is, figure it out. And one of the things we want you to be careful of is we don't want you to have this sort of knee-jerk reaction like, okay, I see a square root, I'm doing trig sub right away. Because that might not be the best thing in some situations. We always want you to be doing what's the best thing. And of course, by best, we mean the one that you're comfortable with and the one that's least likely to make a mistake while carrying it out. Now you might wonder, could you do this by trig substitution? And the answer is, yeah, we could. So we're going to actually go ahead and redo it by doing trig substitution. And we'll see where we go. And, all right. I will say this is the fun part of math, where you get to the place where it's like, you can do things in multiple different ways. And it's nice to know that. Okay, so if we were going to do trig substitution, because after all, we have all this space here, we should do something with it. What would we do? Well, in the square root, we see a variable squared plus number squared. So when we see that form, that tells us the kind of substitution we should make would be the tangent theta. The dy would be secant squared theta, d theta, that's the derivative of tangent, dy, and then the square root of y squared plus 1, and this is why we made our substitution, is so that this will simplify. That's tangent squared plus 1, which is secant squared. When we take the square root, we get secant. All right, so what does this integral become? Well, we get the y is tangent theta. The dy, well, actually, sorry, I skipped. The square root of y squared plus 1 is secant theta. The dy is secant squared theta, d theta. Now, our bounds. Don't forget your bounds. What are your bounds? Well, suppose y is 0. What angle, when you plug it in for theta into tangent of what angle, gives you 0? 0 does. Great. Now, root 8. What angle, when you plug it into tangent, the output gives you root 8? The answer is arctangent of root 8. All right. Great. Beautiful answer. Beautiful answer. Okay, good. Now, you're probably thinking, not quite as nice as what we had before. Well, you might be wondering, can you simplify arctangent of root 8? And no. Arctangent of root 8 is as simple as it can get. Unfortunately, there's not a convenient angle that where you plug it in, you get the tangent of that convenient angle equals root 8. Okay, so how would we proceed in doing this integral? Well, it's one that involves secants and tangents. So when we see secants and tangents, we say, can we pull off a secant squared to the end? And everything left can be in terms of tangent. It's not looking promising because of that single secant there. The other thing is, can we pull off a secant tangent to the end? And is everything left in terms of secant? And then we're like, OMG, excuse my language, but OMG, that's exactly what we have. It's exactly what we have. So this is perfect. You see, so we can think of this tangent theta, secant theta, d theta as our du. In particular, we now make the substitution u equals secant theta. Then that becomes our du. Okay, great. So what do we have? We have the following. This will be equal to the integral tangent theta, secant theta, d theta. That's our du. And then we have our u squared. And now the bounds. Okay, so let's think about our bounds. Now, one bound is pretty straightforward. 0. Secant of 0 is 1. Okay, great. Lower bound, 1. Now, the other bound, secant of arctangent of root 8. That one maybe we should think about. Okay, so secant of arctangent of root 8. So, for a second, let's just say, look, this is an angle. We'll call it an angle name. We've already used theta, so I'll just call it a slightly different angle name. We'll call it alpha. And I say, okay, tangent of alpha is root 8. That's how we picked it, or root 8 over 1. So, draw a right triangle, and tangent, opposite over adjacent. Pythagorean theorem, 1 squared is 1, square root of 8 squared is 8. That makes that 9. If we square that, so that means square root of that would give this side is a 3. Okay, and now, what is secant of alpha? Secant is hypotenuse over adjacent, meaning it's going to be 3. So, we get 1 to 3, integral u squared to u. Well, that's not bad at all. That's 1/3 u cubed. Evaluated from 1 to 3, which is 1/3. 3 cubed, 27. 1 cubed, 1. Or, if you like, 26 over 3. So, yeah, we can do it doing trig substitution. We get the same answers. We should get the same answers because we're doing the same problem. We're just doing them in slightly different ways. But that shouldn't change the outcome. Okay, good. A nice warm-up problem. Well, now that we've warmed up, let's go and do some more problems. Our next problem. Find the integral y squared over 4 minus y squared to the power 3/2 dy. All right, well, what can we do? We look at the form. Now, we don't see an easy substitution, at least I don't see one. And I do see, there's a square root involved because that's what that over 2 in the power means. And so we say, okay, so it's of the form a squared minus u squared. In particular, you see it's 2 squared minus y squared. Now, for a squared minus u squared, the right form of substitution is normally sine. So we'll start there. So it says, okay, u should be a sine theta. So in our case, our u is y, and our a is 2. So we're going to make a substitution. Y equals 2 sine of theta. Well, our dy, derivative of sine, is cosine. So 2 cosine theta d theta, dy. And if we look at the square root of 4 minus y squared. Well, that would be the square root of 4 minus 4 sine squared. And, well, you can pull out the square root of 4 is 2, and the square root of 1 minus sine squared is cosine. All right, so that's all of our pieces together. Now we update. What will our integral become? Well, just go through piece by piece and make sure you keep track of everything. So it's still the integral. Y squared, well, y is 2 sine theta, so 2 sine theta squared. The denominator, 4 minus y squared to the 3/2, well, that's really the square root of 4 minus y squared cubed. So that's going to be 2 cosine theta cubed. And now we're going to multiply that by dy. All right, well, what is dy? Well, dy is 2 cosine theta. So 2 cosine theta d theta. So we've done our translation. Everything has been translated, right? We started with everything in terms of y. Everything now is in terms of theta. And we're actually pretty good, right? Because we see, we have this 2 cosine theta cubed. There's a 2 cosine theta there. So we can actually knock 1 out. Okay, that's great. You'll see we have a 2 squared over 2 squared, which means the 2's will cancel. So we have a sine squared over a cosine squared. And that is not bad at all. Indeed, that would become what? Well, sine squared over cosine squared is tangent squared. All right, well now that seems like a much easier kind of expression to deal with. Well, how do we deal with tangent squared? Well, we reach into our trig identities. So look, tangent squared is not on our list of things we can integrate, but it's close. The way we handle tangent squared is we say, okay, there's an identity. Tangent squared plus 1 equals secant squared, which says, tangent squared is really the same as secant squared minus 1. All right, good. Now, as a side note, we'll write that down just so, in your case, wait, why? What? That's our identity, tangent squared plus 1 equals secant squared. That's what we're using in that step right there. Okay, and now we're ready to integrate. The integral of secant squared, it's on our list, is tangent. The integral of 1 is theta. It's an indefinite integral, so plus c. So we're almost there. What do we need to do? Well, we need to figure out what is tangent theta and what is theta. Now we could do some various things with, we know what sine is, we know what cosine is, we can divide. And that would give us the right answer, but we can also just draw the picture, right? We say, look, sine of theta, if we move things around, is y over 2. So I'm just dividing both sides by 2. So draw a triangle, put theta in the corner. Sine is opposite over hypotenuse, which means your adjacent side is the square root of 4 minus y squared. So tangent of theta, opposite over adjacent, we end up with y over the square root of 4 minus y squared. Great. And now what about theta? Well, that's not so bad either, right? Look, there's the theta right there. Just got to get out of the sine. So we do inverse sine. Or I prefer to put arc sine, just because less likely to lead to confusion. Arc sine, y over 2 plus c. And we're done. See? It's not so bad. Once you know the right form, you translate the problem, and you say, once I'm in trig, I've got tools. I've got identities, and that can help me solve these integrals. And of course, it's going back at the end, but practice, right? Practice with the triangles. Knowing how trigonometry relates to triangles, it's very important so that we can say, hey, we know how these things work. We know we know. All right, good. Well, let's keep going. Our next problem. This will definitely be a good one. Evaluate the integral from 0 to 3 of x squared square root 12 minus x squared dx. All right, a definite integral. Okay, good. Well, what's going to happen? What's going to happen? Well, let's be careful and see what we can say. Well, it's not really good for normal substitution, see, because of the fact that's an x squared there. If it was just an x, we'd say, okay, normal substitution, away we go, life is good. But it looks pretty reasonable for trig substitution because we see a number minus a variable squared. We say, okay, great. So when we see something of the form a squared minus u squared, which is what we see here, then what happens? Well, that tells us, hey, that's a substitution of the form u equals a sine theta. Now, what do we need to do? Well, we need to figure out, okay, what do we have? Well, in our case, it's 12 is the a squared. Okay, that's kind of a weird thing, but all right, we'll work with it for right now. So we'll think that square root of 2 squared minus x squared. Okay, so x equals square root of 12. All right, that's interesting choice. Sine theta. Okay, so there we go. Now, by the way, square root of 12, there is a little bit of a square inside of 12. See, 12 is 4 times 3, so square root of 12, we could write that as 2 root 3 sine theta. Now, of course, we see the root 3, and that piques our interest, like, sine has an interesting angle that involves a root 3. I wonder if that will come into play. Well, who knows? We gotta keep going forward. We won't know until we get there, and so let's keep moving forward. All right, what can we say about our dx? Well, our dx would be 2 times square root of 3 times cosine. All right, and well, what else? Well, the square root of 12 minus x squared, that's really the square root of 12 minus 12 sine squared. Okay, well, look, you can pull out a square root of 12, and then you get 1 minus sine squared, cosine squared underneath the square root, which comes out as cosine. All right, so there's all of our pieces. We know how to update all of our pieces. Well, what do we get? Okay, this will become the integral x squared. So square that would be 12 sine squared. Okay, square root of 12 minus x squared. Well, square root of 12 times cosine. All right, dx. Well, that's actually 2 root 3, as we said. I'll write it again as square root of 12 just to make things compatible, times cosine theta. And whoops, I can see I forgot to write something down. That's all right. Through the wonder of editing, we should have had a d theta there. And I know you're thinking, Steve, that's just notation. Come on, are we really going to be that particular? We should be. We should respect notation. Because the further we go, the more we see notation isn't just for deducting points on quizzes and exams. Notation actually plays an important role. And this especially comes up when we hit multivariable calculus. So it's good to get into the habit of good notation when we're still young. I like to think I'm still young. I know you are. So let's make sure we follow those habits. Now, this is a definite integral, so we need to worry about the bounds. And it's useful to worry about the bounds because the nice thing is when you have a definite integral, if you keep updating the bounds, you always get to keep going forward. And you never have to go back. So if we update our bounds, we never at the end have to go back in terms of x, which can save us work. On the other hand, if we don't update the bounds, we have to head back a couple steps. So it's always best to update the bounds. And I know sometimes it gets annoying, but it's a good habit to be into. Okay, so let's think about the bounds. So remember, our current bounds are x bounds. So like x equals 0, x equals 3, we want to go to theta bounds. Theta equals something to theta equals something. So we think about what's going on. So we plug in x equals 0, and we say, okay, well, 0 should equal 2 root 3 times sine of theta. All right, well, that really says, look, sine of theta better be 0. Do we know an angle where the sine of the angle is 0? I know one. You know one too, right? And we can all say it together, 17 pi. Oh, wait, no. I meant 0. Yeah, 0. 0 is the one you should use. You should always use the small one. Yeah, 0. Good. Okay, other bound, right? There's an upper bound as well, right? Okay, good. So we plug in x equals 3. 3 equals 2 root 3 sine theta. Okay, well, that's the same as saying sine of theta. If we divide both sides by the 2, that's easy. When you divide by the root 3, you'll have a 3 over root 3, which you can simplify to root 3. So we have root 3 over 2. Now, that's a really good thing. We have seen sine of theta equals root 3 over 2 before. I really hope you have. And it's one of our nice angles. And in particular, it's 60 degrees. Or, because we're doing calculus, pi thirds. So, our upper bound is pi thirds. Wow, beautiful, beautiful. It's like they wanted us to have a nice upper bound. Because they did. They picked it that way. Oh, no surprise. They loved us. They loved us. Okay, good. Now, let's continue forward. So, what do we have? Well, we have a 12, and a square root of 12 and square root of 12, which is another 12. And 12 times 12, it's a little bit gross. Ha ha ha. Silly math humor. No, it's 144, right? A dozen is known, there's a word for it. It's called a gross. So, okay, 144, that's the constant. We'll put it off to the side for a second. Integral from 0 to pi over 3. And sine squared cosine squared d theta. Okay, so we have sine squared cosine squared. Well, both the powers are even. So time to do power reduction. Okay, great. Wow, good problem. Now, how does power reduction work? There are 3 identities that relate to power reduction. And they are as follows. They are that cosine squared is 1/2 1 plus cosine 2 theta. Sine squared is 1/2 1 minus cosine 2 theta. And sine times cosine is 1/2 sine of 2 theta. So those are the 3 identities that relate to power reduction. And among them, I really strongly encourage people to use the sine times cosine as much as possible. I find it's very helpful because notice what it doesn't have. There's no adding or subtracting going on. So, for instance, we can say, okay, this is the same as 144, integral from 0 to pi over 3. And we really have sine times cosine squared. So this becomes 1/2 sine 2 theta squared. So I'm applying this power reduction to there. Now, 1/2 squared is 1/4 times 144. Well, 144 divided by 4 is 36. Okay, so now we have 36, integral 0 to pi over 3, and we have a sine squared of 2 theta. Well, still, even power reduction again. So now we'll use the sine squared one. So that'll be a factor of 1/2, then 1 minus cosine. And this is the part where I know in the past I've made mistakes, so I pause, so I help myself not make the same mistake. And I say, well, okay, remember, come on, Steve, don't forget, you got to double the current angle. So it's, see, we're doing sine squared of 2 theta, so I've got to double 2 theta, which means it'll be 4 thetas. So there's a 4 theta that goes there. All right, good. Disaster averted. Okay, 36 times a half makes this 18. And now we can look, we can integrate. Perfect. Integral of 1 theta. Integral of cosine is sine. It's still going to be the same minus. And the other thing we have to worry about, okay, if because of the 4 here, we need to divide by 1/4. Good. And evaluate from 0 to pi over 3. All right, we're almost there. Almost. What's left? Well, what we need to do is figure a couple things out. When we plug in 0, the good news is 0 is 0, and sine of 0 is 0. So, whoosh, gone. Gone. Okay, so plug in pi over 3. So we're going to get 18 times pi over 3 minus 1/4 sine of 4 pi over 3. Well, if we just knew what 4 pi over 3 was, we'd be good to go. Well, let's draw ourselves a picture. And we said, look, pi over 3 is this 60-degree angle. And what would 4 pi over 3 be? Well, it'd be that pi over 3 plus pi. So it'd actually be directly across. So if you think about the y values, which is the sine, the 4 pi over 3 has the same y value, except we flip from positive to negative. So sine of 4 pi thirds, since we know that sine of pi thirds is what gave us the root 3 over 2, this would actually be a minus root 3 over 2. So, all right, if we finish off by multiplying the 18 through, 18 divided by 3 would give us 6 pi. And then we can say we have 18. Minus minus makes a plus. So there's a plus. We can cancel off a single 2. So we end up with 9 root 3 over 4. And that would be our answer. Okay, right? Again, we can talk. 18 times pi thirds, 6 pi. And then here, 18, take the 2 in. That leaves us with the 9. You have the 4th and the root 3. Minus minus makes plus. So 6 pi plus 9 root 3 over 4. A beautiful answer. And notice we didn't have to go back in terms of x. What would we have to have done if we did have to go back in terms of x? Well, because of that 4 theta, we'd have to say, okay, well, sine of 4 theta is 2 sine 2 theta cosine 2 theta, and then we'd have to repeat it again, and we'd be unraveling for quite a while. And so it actually was great because it's a definite integral, and because we updated our bounds, it made it so much simpler for us to carry out the evaluation. Good job, us. Good job, us. What a beautiful problem. Good. Well, let's keep going. Lots of beautiful problems still to go, right? Of course, of course. Our next problem. Find the integral dt divided by 2t minus t squared to the power 3/2 dt. Okay, well, all right. First off, we got a little bit too excited with our dt's. So we'll fix that in post-production. Okay, we only need one dt. All right, there we go. Now, second off, it kind of feels like trig sub, right? Because we see that there's a square root there. But it kind of doesn't feel like trig sub, because in trig sub, we should have like a number plus a variable, a number minus a variable. There shouldn't be variable. It should always be number variable combination in some way. So the fact that we see a 2t minus t squared is not very promising right now. Well, or rather we should say, of course, we need to do some work before we can talk about trig sub. It's not ready for us to go trig sub. We can't say, oh, that's u and that's a. No. A has to be a number. It can't be anything which is changing. So we say to ourselves, okay, we know in trig sub, the way it works is we have something squared, our variable squared, and we say, well, there's not a square yet, but there's like pieces of a square, a t squared and a 2t. So it'd be nice if we could complete the square. Oh, yeah, okay, all right. I see where you're going. Being a little bit coy there. Oh, complete the square. Exactly, okay. So here's what we're going to do. We're going to focus on a way to rewrite this 2t minus t squared as something number squared, variable squared combination. Okay, so let's start with the 2t minus t squared. I'm going to think of that as minus t squared minus 2t for right now. I always prefer to have the coefficient of that t squared be 1, because that's the way we do complete the square, is when it is 1. If it's not 1, you have to be a little bit careful about what comes afterwards. So we just make it 1 for the time being. We'll fix this in a second. Okay, so now according to complete the square, what would we need to add there? Well, divide the middle term by 2 and then square it. So we need to add 1. And now we're like, oh, this part is nice. That's t minus 1 squared. But we got to be careful. We added 1. So if we add 1, we're going to do our immediate subtract 1. See, if you add then immediately subtract, you've undone what you've just did, which is net change of 0. So subtract 1. Okay, so now if you put the minus back through, minus 1 is 1, and then minus t minus 1 squared. So our original integral becomes the integral dt over 1 minus t minus 1 squared to the 3/2 power. And now we're like, that feels more trig sub, because we do have variable squared, that's the t minus 1 squared, and number squared, it's the 1 squared. Okay, well, so what's the correct substitution to be making here? Well, in our case, we say, all right, it's an a squared minus u squared. All right, well, we've seen this a lot today. Well, not surprising, there aren't that many variations, right? U equals a sine theta. So in our case, it's 1 squared minus t minus 1 squared. So we're going to let t minus 1 equal sine theta. Taking the derivatives, dt, derivative of sine, cosine theta, d theta. And now the square root of 1 minus t minus 1 squared, well, that's the square root of 1 minus sine squared, which is the square root of 1 minus, the square root of cosine squared, becomes cosine theta. All right, great. So our integral becomes, in the numerator, our dt is cosine theta d theta. And now this 1 minus t minus 1 squared to the 3/2, well, that's a square root cubed, that's cosine cubed. Okay, wow. Cosine over cosine cubed, you almost couldn't ask for a better thing. You can cancel off a single cosine, and then you have a 1 over cosine squared, that's secant squared. It's almost like it was meant to happen, because that's on our list of things we know how to integrate. So the integral of secant squared is tangent. So now we have tangent theta. Of course, plus c. Well, we're almost done. What's left? Well, we've got to figure out what is tangent. Now, the way we can do that is go back and say, well, look, we know sine of theta is t minus 1, which we can think of as t minus 1 over 1. So we form a triangle, and here's our angle. And we say, all right, our opposite over our hypotenuse. So the missing side would be the square root of hypotenuse squared minus the adjacent side squared. But wait a second, we have a name for that. That is, whoops. Okay, that's a little sloppy there. Square root 1 minus t minus 1 squared. That's what we started with. So it's really the square root of 2t minus t squared. And now we're almost done, right? So what do we see? Well, we're going to take tangent is opposite over adjacent. So opposite over adjacent will give us our t minus 1 over the square root of 2t minus t squared. And that will be plus c. And we're done. That's it. That's it. Wow. Great. That one was wonderful. We should have more problems like this. One can hope, right? One can hope. So let's try some more problems. Let's see, can we have more hope? All right. Find the integral square root of 21 plus 4x minus x squared over x minus 2. Now, we're actually kind of in a similar situation to where we were before. We say our square root is there, so we're thinking maybe trig sub, but it's not quite as, some variable part squared. And when I say a variable part, I just mean something which varies, that has a variable inside of it. So it's not a variable squared and a constant squared in some way. It's not written like that. So if we do want to pursue trig substitution, and to be honest with you, I don't see how to do it without doing trig substitution, we've got to take some time to rewrite what we have. So let's take some time to rewrite what we have and see what we end up with. Okay, so we have 21 plus 4x minus x squared. We're going to work on rewriting that. So I'm going to start with the x part. So I'm going to pull out a minus, and then I have x squared minus 4x. And now, because I pulled out the minus so that the coefficient in front of x squared is 1, which is important, it's not so bad to complete the square. If we complete the square here, minus 4 divided by 2 is minus 2 squared, means you would add 4. Well, now I'm going to subtract 4 right away, and of course I'm not going to forget there was a 21 at the start. Okay, good news is this part right here I can combine together as a nice square. And as a bonus, I see, there's a hint we're on the right track, right? Because what do you see? You see, x minus 2, that's an x minus 2. They're very close. So they probably are connected. Okay, so we're feeling good about that particular substitution. Or rather, I should say that particular rewriting. The substitution is still to come. And so what do we have here? Well, I'll do the constant because you have a minus 4, which is positive 4, plus 21, which is 25. Oh, that's a square number. Wow, cool. I'll go ahead and write it as 5 squared. And then minus x minus 2 squared. Perfect. Great. So if we update, look, our integral is now the square root of 5 squared minus x minus 2 squared divided by x minus 2 dx. All right, well, from here, where do we go? Well, we see, look, it's of the form a squared minus u squared. So our substitution is going to be a sine theta. In our case, because it's 5 squared minus x minus 2 squared, that says we should make x minus 2 is 5 sine theta. Okay, well, so we get dx is 5 cosine theta d theta, and this expression, well, more particularly, 5 squared minus x minus 2 squared, well, that'd be 5 squared minus 5 cosine theta squared, 5 sine theta squared, excuse me. The 5 squared, so you can pull all the way out front, and so you end up with the 5, and the square root of 1 minus sine squared is cosine squared, and after you take the square root, it just becomes cosine. Okay. So all of our pieces are ready to go. Now, what can we do? Well, from here, we can do the following. Let's see what we get. We get this is equal to the top piece here is 5 cosine theta. The dx is 5 cosine theta, d theta, and the x minus 2 is 5 sine theta. All right, well, good. This is actually not bad, right? We can say, okay, pull out, cancel a 5, pull a 5 out, and so we get this is 5. And what can we do here? Well, it's a cosine squared over sine. Okay, so we can write that as cosine squared. I can replace as 1 minus sine squared over sine. And then we can say, well, look, that's the same as 1 over sine, which is cosecant, and sine squared over sine, which is sine. And there we go. There we go. Now, this is where things get interesting. You can say, all right, we've got kind of two choices. One is, do we remember the integral of cosecant? Now, normally that's not on our list of 10 things we need to know, and so we're very like, oh. But let's suppose for a second we did remember the integral of cosecant. It turns out that the integral of cosecant is the following. It's a lot like the integral of secant, and you just have to sort of say, okay, just remember that there's sort of, you flip things around. It's sort of like a co thing going on. So the integral of cosecant would be a natural log of cosecant plus cotangent. If you think of the integral of secant, it's secant plus tangent in the natural log, but a minus. And the integral of sine, well, is negative cosine. There's already a minus, so it's a plus a cosine. And then a plus c. Okay, so we can do that. That's a perfectly valid option. And well, let's finish up doing that, and then we're going to say, or we could have done something slightly different. Okay, so how do we finish up? Well, we can draw our triangle, and let's see, what is our triangle? Well, we can use this for our triangle. So sine of theta is x minus 2 over 5. So if we come here, there's theta. Sine is opposite over hypotenuse. And then this missing side, well, you take 5 squared, subtract x minus 2 squared, which is actually this original piece here. That's not too surprising. That's because we set it up so that that term does show up as part of a triangle. So, cosine. Well, cosine would be adjacent over hypotenuse. So it'd be this term, square root of 21 plus 4x minus x squared over 5. But we're timesing that by 5, so that would give us square root of 21 plus 4x minus x squared. Okay, that's our 5 cosine theta. Minus 5 natural log Okay, cosecant. What's cosecant? Well, it's the opposite of sine. So sine is opposite over hypotenuse, so cosecant would be hypotenuse over opposite. 5 over x minus 2. And then cotangent. What is cotangent? Adjacent over opposite. So plus square root of 21 plus 4x minus x squared over x minus 2 and plus c. Okay, now there are some things you could do. You could break the log apart if you wanted to. We're not going to go through and do that exercise. That's not our goal for right now. Our goal for right now is just to say this is something that can be done. Now, what if you got to this point and you're like, oh, I don't know how to handle the integral of cosecant. What do I do? This is kind of an interesting thing that can happen. So if you get to a certain point and you're like, wow, you know, if I could just sort of change things. So if I had not cosecant but secant, I'd be happy. It turns out there's an easy way to do it. Unfortunately, it means a lot of backtracking. So what do you do? Well, what you do is you go all the way back to your original substitution. And you said, look, the original substitution was a sine theta, or you could have chosen a cosine theta. And what happens is if you switch to a cosine theta, then what will end up happening is, well, there's a lot of things that end up happening. But for example, the dx becomes sine. This square root of 5 squared minus x minus 2 squared becomes 5 sine. So wherever you see a sine becomes a cosine, wherever you see a cosine becomes a sine. And so it would have, if you followed it through, become the following. It would have become the integral of 5 sine theta minus 5 sine theta d theta divided by 5 cosine theta. Now, you might say, where did that minus come from? The derivative of cosine would be negative sine. That's why we don't make the substitution of cosine in a typical setting. But that's the only change, is that extra minus there. Then the sines becomes cosines, the cosines become sines. And now you say, wow, this is actually great. Because if you simplify this expression, this would become 5 integral cosine minus secant. And now you have something you'd feel happier to work with, and away you could go. So that's your sort of your two options. If you get to a place where it's like, oh, cosecant, well, the integrals of cosecants are essentially the integrals of secants, but throw in a minus. Same with cotangent. The other thing is like, well, okay, I'm not happy. I want to flip it from a cosecant to a secant. Let me backtrack to my substitution and choose the other substitution to make. So those are your two options. Okay. Well, anyways, there you go. Great. Wonderful. Well, another problem down. We should do more problems, though. All right, our next problem. Find the integral of x cubed over 4x squared plus 1 to the 3 halves dx. All right, well, okay, this looks interesting. The nice thing is it's pretty well set up, and we can proceed. Now, we could actually go in two different options here. This problem potentially can be done with trig sub or without trig sub. And well, let's try it with trig sub first, and then we can say, well, what would happen if we hadn't done trig sub, and what would have been the procedure? And how can we spot, oh, trig sub isn't required here? So let's take a look. If we are thinking trig sub, our cue here is, oh, I see something varying squared plus numbers squared. And I say, all right, that's how the form u squared plus a squared, which tells us our substitution should be u equals a tangent theta. Now, more precisely, we have a 2x squared. So I'm remembering I got to square that, that 4 needs to be 2 squared, because I need to write it as something squared. So 2x squared plus 1 squared. Okay, so I can say 2x should be tangent theta. All right, that's our substitution that we want to make. All right, so what does that tell us? Well, among other things, we can also write this as x equals a half tangent theta if we wanted to. And now just go through, do things, for example, dx, derivative of tangent, secant squared. All right, how about 4x squared plus 1 to the 1/2? What would that be? Well, 4x squared is tangent squared. Tangent squared plus 1, secant squared. And square root of secant squared is secant. So we get secant. Okay, so this integral becomes, okay, our x cubed, 1/2 tangent theta cubed. Our dx, 1/2 secant squared theta, and whoops, forgot the d theta again. D theta. Downstairs, this 4x squared plus 1 to the 3/2, well, that'd be secant theta cubed. Okay, and there we go. There we go. That's the integral that we need to work on. Okay, so, well, what can we do here? Well, we have a half cubed times a half, which would make us 1/16. And then we have a tangent cubed. All right. And there's a secant squared. And here, secant cubed. So over secant. Okay. So that's our integral. So we have to think about, okay, how would we go about doing this integral here? Now, there's actually a couple ways to do it. And so it just is a matter of which way do you prefer. We could do it and stay inside everything in terms of secants and tangents. Okay, well, let's suppose we did that. What's the other alternative? So just to be clear, the other alternative is put everything in terms of sines and cosines. It'll be a very, very similar process here. So I'm not going to like, there's a clever trick here. Both would be about the same. So when I see things involving secants and tangents, I say, well, what I can do is I can try to either pull off a secant squared to the end and write everything else in terms of tangent, which looks like it would be a little bit challenging to do that. Or I can pull off a secant tangent to the end and try to write everything else in terms of secant. Now, the nice thing is, because of that tangent cubed, if I pull off a secant tangent to the end, I'm pulling off just one of those tangents, which would leave me with the tangent squared. And in the back of our minds, we kind of have this mantra, tangent squared is a lot like secant squared. They're almost interchangeable because there's this beautiful identity that brings them together. So I'm going to try to do this. I'm going to try to pull off a secant tangent to the end. So how would I succeed? Well, there's a 1/16, and there's going to be a tangent from that tangent squared. Okay, sorry, tangent cubed, so there's a tangent squared left. And so there's going to be a secant tangent on the end. All right, so this tangent came from that tangent cubed. Where did the secant come from? You say, well, there's no secant on the top to pull from. So how do we pull a secant out of nothing? Well, the answer is we kind of pull it off the bottom by making it secant squared. You can check. What happens here? Well, if you have a secant over secant squared, that'd be a single secant left. So these are equal to each other. Another way to think about it is I multiplied top and bottom by secant, and that's how I got my secant upstairs, but it had me add a secant downstairs as well. Now, what can we do with the tangent squared? Well, tangent squared is the same as secant squared minus 1. So, we get secant squared minus 1 over secant squared. Then we have our secant theta, tangent theta, d theta. All right, now we can even go a little bit further. Okay, so this is 1 over 16, and we're going to get 1 minus, I'll write it as secant to the minus 2. It's 1 over secant squared times secant theta, tangent theta, d theta. And now we're ready to really finish up, do our substitution. And we say, all right, let u equal secant. And if we do that, du is secant tangent. And we say, wow, this is a really clean integral. We get 1 over 16 integral 1 minus u to the minus 2 du. Okay, so that's 1 over 16. And then here, integral of 1 is u. The integral of u to the minus 2, well, that's u to the minus 1. I can write that as 1 over u. And I have to divide by a minus. So originally it was being subtracted, so subtracting a minus makes it a plus. And there we go. Now we just got to work our way backward. Well, we say, okay, u is secant. So what we really have here is secant and 1 over secant. 1 over secant has a great name. It's called cosine. So this is 1 over 16 secant plus cosine plus c. Now we have to say, okay, what is secant and what is cosine? Well, actually, we know both of them because secant, look, it's right there. Square root of 4x squared plus 1. And so what is cosine? It's 1 over that. So we end up with 1 over 16 times the square root 4x squared plus 1 plus 1 over the square root 4x squared plus 1. And we're done. That's it. Now, I said you could do this in another way. By the way, you could get a common denominator if you wanted to. You can also rewrite that if you get a common denominator. That would be 4x squared plus 1, which makes it 4x squared plus 2 divided by 16 times the square root of 4x squared plus 1. And then here you can see, you can cancel off a 2. So you could also write this as 2x squared plus 1 over 8 times the square root of 4x squared plus 1. Now, what's the non-trig sub way to do this problem? And how would we even spot it? Well, you sort of say, okay, what if I just substitute on the inside? What would happen? Well, the derivative of 4x squared plus 1 would essentially be x. We don't worry about the constants. Those are details which we worry about when we need to worry about. So it would be x. Say, well, I have x cubed. Let me say, wait, this is good. I can pull off a single x and say that's going to become part of the x dx and be left with an x squared and say I can replace that in terms of u. So this problem can also be done without any trig sub at all, and it would go like this. And what would happen, you say, okay, you'd say let u be this inside. So if you let u equal 4, let's make it a w just so we don't confuse ourselves. So I mean, w is like when we're going to double down, right? We're not just going u, we're going w. All right, although w, yeah. All right, so w is 4x squared plus 1. So that says dw equals 8x dx. All right, put it across. 1/8 dw is x dx. So what happens? Well, we have our integral of x squared over 4x squared plus 1 to the 3 halves times x dx. Well, we can see what happens. This downstairs becomes w to the 3 halves power. What about x squared? Well, x squared, if you take that, that's 1/4 w subtract 1, because you would subtract 1 divided by 4. So we have integral of 1/4 w minus 1, that's our x squared. 4x squared plus 1 to the 3 halves downstairs becomes w to the minus 3 halves. X dx becomes 1/8 times dw. All right. Making good progress here. And what do we see? All right. That would be, well, 1/4, 1/8 pull out, 1 over 32. And then we'd have the integral of w to the minus 1/2, which is that term. And then minus w to the minus 3 halves. Okay, dw. Well, that's 1 over 32. And when we integrate here, well, that would be w to the 1/2 times a 2, because we have to divide by 1/2. And then minus, here would be w to the minus 1/2. And then you divide by a minus 2, so same. Well, divided by minus 1/2, same as multiplying by minus 2. And then, of course, plus c. Okay, so we end up with 1 over 16, because you can pull the 2 out. And then what do you have? W to the 1/2. Square root 4x squared plus 1. W to the minus 1/2. 1 over square root 4x squared plus 1. And plus c. And you might say, hey, wait a second. That sounds familiar. Yeah, very familiar. Almost like we had done it before. And so there are other ways to do it. And oftentimes you can get to the end of a problem, and if you see like there's no arc sine or arc tangent or arc secant floating around, it means that if you were clever, you probably could have massaged your original equation in some way, shape, or form and done your integral. Does that mean trig substitution is a bad idea? Not at all. It just means that there's alternatives. You should always say, let me do the thing I'm comfortable with because I want to succeed. My success is important to me. That should be your mindset going in whenever you're solving any problem. How do I do this problem so that I can succeed? All right, good. Whew. I'm glad we got the same answer, by the way, because getting the same answer is a wonderful sign that we're doing things correctly. I like it when we do things correct. It feels so much better. All right, well, let's keep going. Find integral y squared over 1 plus y squared to the 3 halves dy. This will feel really similar to the one we just did, except the power upstairs is a square. So this one is not set up for a non-trig substitute. It really says we're feeling the trig sub on this one. There's not a clever thing to do. Or at least there's not an obvious clever thing to do. Sometimes there's some clever things which are not obvious. Well, we don't want those. That's terrible. We're not here to be clever. We're here to be methodical. We're here to solve problems. Okay, so this looks like there's not really any big surprises. And what do we see? Well, we see a squared plus u squared. And we say, okay, look, that's really setting us up well. That's when we make our substitution. U equals a tangent theta. In our case, 1 squared plus y squared tells us we should be substituting y equals tangent theta. dy, derivative of tangent, is secant squared. And the square root of 1 plus y squared, or if you like, 1 plus y squared to the 1/2. Okay, that's 1 plus tangent squared is secant squared, and that becomes secant. Okay, so substituting in all our pieces. Y squared, tangent squared. dy, secant squared, d theta. And 1 plus y squared to the 3/2 is secant cubed. All right, there we go. That's it. That's what we have to integrate. Well, what can we do? We get to something kind of similar to what we had last time, right? We have what? Tangent squared over secant d theta. Now the problem is, unlike last time, this is not well set up for pulling off a secant tangent. But that's okay. You might say, well, why isn't it not well set up? Well, if you pull off a tangent, so you have that tangent squared, right? So if you pull a tangent to the end, that'll leave you with one tangent left over. And a single tangent is not good for substituting. You really want to have two of them. But we still have our nice identity that involves tangent squared and secant. And so we can say, okay, look, tangent squared, we know that. It's another way to say secant squared minus 1. Okay, great. So how do we do that? Well, secant squared over secant is secant, and that we can handle. 1 over secant is cosine, and that we can also handle. And so we're like, woohoo, nice, things we can handle, yeah. All right, integrals that we like for 500, Alex, these kinds of integrals, ones that we can do. All right, well, integral of secant, log of secant plus tangent. Integral of cosine is sine. And of course, plus c. All right, so the last thing to do, we've got to go back to y. We started with y, we must end with y. It's an indefinite integral. All right, well, we start by saying, look, we know what tangent of theta is. It's y. Okay, that's good. So that handles that part. But we also say, look, that's the same as y over 1. So we draw our triangle, theta, opposite over adjacent. So that missing side is the square root of y squared plus 1. Okay, great. What's secant? Secant is hypotenuse over adjacent. So square root y squared plus 1. What's sine? Opposite over hypotenuse. So this will become y over square root of y squared plus 1. So our answer, we have log of square root y squared plus 1 plus y minus y over square root y squared plus 1 plus c. And we're done. Wow, cool. Look, what a small difference a 3 makes. Changes the answer, right? Last time it was 3, now it's a 2. Our answer is very different. And that's okay. It's wonderful, really. Just shows you the beautiful menagerie that is doing integration. Well, let's keep going. All right. Our next problem. Find 1 over the square root 4y squared plus 8y plus 3 dy. Oh, okay. This should be interesting. Now, we see it's kind of similar to the things we've done earlier. We say, okay, it looks trig sub. You know, it just feels that way. It's a square root. The problem is it's not quite set up correctly. For it to be trig sub, we really need to say, all right, we need to have something varying squared and some constant part. And usually we think of it constant squared in some appropriate combination. So what we need to do is say, if we're going to do trig sub, we've got to first get it to that point. All right, so what can we do? Well, looking at this part, well, we can pull out a 4 out of the y squared plus 2y. Okay, now why do I pull the 4 out? Well, oftentimes if I don't see a nice variable thing square, I say, well, I want to make a square. Or another way to put it, I want to complete the square. So it's like I have part of a square, I just need to go all the way. So I'm setting myself up to do complete the square. And in complete the square, you want a 1 in front of your quadratic term. So that's why I'm pulling the 4 out. So I say, okay, what would I need to add to get here a nice perfect square? I need to add 1. Okay, so that would give us y plus 1 squared, which is great. But let's be careful here. So this would be 4y squared plus 8y plus 4. We're supposed to have 4y squared plus 8y plus 3. So how do I change this? Because this is not the same as this. Not yet. It's off by 1. It's a little bit too big. So subtract 1. And now we're like, perfect, perfect. So it's of the right form. This has become the integral of 1 over the square root. We could even really put in the 4 as like a 2 squared. So it's 2 times y plus 1 squared minus 1 squared. All right. Well, now we start thinking, what's the right kind of substitution that we should be making here? What do we need to do? Well, what do we have? We have variables squared minus numbers squared. All right. Now, in that kind of substitution, this is where we want to substitute in secant. So, in our case, we have 2 times y plus 1 squared minus 1 squared. So we say, all right, 2 times y plus 1 should be equal to secant. Well, let's go through and see what happens. That says 2 dy is equal to derivative of secant, secant times tangent, d theta. What else? Well, the square root of 2 times y plus 1 squared minus 1 squared. Well, that's secant squared minus 1. That's tangent squared. And when we take the square root, we're going to get tangent. All right, so we can now identify what's going to happen to these pieces here. And we say, great, let's carry out our substitution. So we get the following. This is going to be equal to the dy. Well, I should bring the half across. So I'm going to have a half. There's a secant theta, tangent theta, d theta. Divide by, downstairs, what do we have? Tangent theta. All right. Well, no problem. And, oh, wow, that's great. Tangent thetas cancel. So it's the integral of secant, which we know. So we have perfect. This is 1/2 of log, and the integral of secant is secant plus tangent plus c. And to finish up, we just have to say, well, look, we got to get everything in terms back of y. But we know how to do it. We actually wrote it down. So we have 1/2 log. Okay, what's secant? Well, secant is 2 times y plus 1. So 2 times y plus 1. And now plus, what's tangent? Well, it's this square root thing here. And we say, well, wait a second, that really came from here. So this square root thing is, that's tangent. So plus the square root of 4y squared plus 8y plus 3. And done. Ah, good. Wow, we're picking up speed. We must be getting better. I hope so. I mean, we're putting in our time, right? As we put in our time, we get better. That's the way that math works. The more that you do, the better that you get. So, all right. Well, good. Let's keep going. All right. on to our next problem, and it's going to definitely be a problem. Definite integral one. Okay, find the integral 2 to 7 of dx over x squared, square root of x squared minus 1. Okay, so, well, it definitely looks like trig sub, but I don't think there's a simple way to do it without trig sub. And we take a look and say, okay, well, the format we see is the part that varies squared minus number squared. And when we see that, that says, look, you should be thinking of the substitution secant. Okay, so for us, our x squared minus 1 squared says x should be secant theta. Okay, so what do we have? We clean this up. We'll say dx, derivative of secant, secant tangent. All right. And square root of x squared minus 1. Well, that's secant squared minus 1, which is tangent squared. Square root of tangent squared is pretty nice. It's tangent. Great. Wonderful. Now, what do we do? Well, it is a definite integral which has the bound. So we could go through and update the bounds. I hesitate a little bit here on this one because we'd have to have nice numbers. So like, there's not a nice number where secant equals 2, is there? Actually, there kind of is, but shh, don't tell anybody. But there's also not a nice number where secant equals 7. And so let's just do the indefinite integral. I know, I oftentimes say, no, don't do that. But this one time, just because we're friends. But we should also point out that it can be done this way. Okay, so if we did this by saying, let's do the indefinite integral first, say, all right, our integral dx over x squared, square root, x squared minus 1. Well, the top becomes secant tangent. The bottom, well, x squared, secant squared, square root of x squared minus 1 is tangent. We say, whoa, wow, look at all these cancellations. We can get a tangent to cancel, which is nice. We can also get a secant to cancel, which is nice. And so that what we're left with is 1 over secant. Well, that has an even nicer way to write it. 1 over secant is cosine. All right. Well, we can integrate cosine. That becomes sine. Now, we're not out of the woods yet. We have to say, okay, what is sine? Well, we know secant is x. Well, it's really x over 1. So, if we come here and we draw our triangle, secant is hypotenuse over adjacent, which means that the opposite is x squared minus 1. So our sine is the opposite over the hypotenuse. So we end up with the square root of x squared minus 1 over x. Okay, now that's not our answer. That's if we were saying, oh, what if we did this integral just as an indefinite integral? But we have a definite integral. So now what we do is we say, let's take this knowledge and go back to our original problem. And we say, look, this is the same as doing the square root of x squared minus 1 over x from 2 to 7. All right, well, let's think about that. See if we can simplify it. Plug in 7. 7 squared, and that'd be 49. Subtract 1 is 48. So we get the square root of 48 over 7. And then 2 squared is 4. Subtract 1 is 3. So subtract square root of 3 over 2. Now you might say, okay, well, that's as far as we can get, right? Let's see if we can't poke a little bit further. Square root of 48. What is 48? It's 16 times 3. And 16 is a nice square number. So we could say, oh, that's the same as 4 root 3, because I'm taking 16 times 3, and then the square root of 16 is 4. So that's where that 4 is coming from, over 7 minus root 3 over 2. They say, hey, they both have square root of 3's. Well, that's great. We can pull that out. And then we say, okay, if we wanted to combine, common denominator would be 14, right? So it would be 8 over 14, because 2 times 2. And then minus 7 over 14. You have to do 7 and 7 times square root of 3. So we end up with 1/14 times square root of 3. And we're done. We're done. Wow, what an interesting answer. It actually is amazingly compact. You know, oftentimes we're not able to combine terms together when our numbers are not so pleasant to start with. But it worked out really well this time. Cool. All right. Well, let's keep going. Lots more fun problems still waiting for us to do. And what's next? Well, it's the following. Find the integral dx over x to the fourth square root of x squared minus 1. Well, it feels really familiar, right? It's almost like the last one. Almost. It's a higher power, x to the fourth. But we see the setup is very similar in terms of, okay, we see our variable squared minus our constant squared. So that says our substitution should be of the form secant. In our case, because it's x squared minus 1 squared, x should just really be secant. And we get dx secant times tangent. All right, great. And the square root of x squared minus 1. Secant squared minus 1 is tangent squared. Square root of tangent squared is tangent. All right, so those are our pieces. And when we put them in, what do we get? Well, we get the following. We get this is equal to secant times tangent upstairs. All right. Downstairs, we're going to get a secant to the fourth. Okay, whoo, that's a lot of secants. And then a tangent, single tangent. Okay. All right, well, we do have some good news. We get a little bit of cancellation. The tangents cancel, and we can cancel a single secant. So we really have a secant cubed downstairs, but we can flip it over, and so that would become the integral of cosine cubed. All right, well, now we say, how do you integrate cosine cubed? Well, it's cosine to an odd power. We like odd powers, because what we can do is we're going to say, oh, that's like cosine squared times cosine. So we're pulling off a cosine to the end. That cosine on the end will become, setting ourselves up for a good substitution. Now that cosine squared at the start, we got to say, well, rewrite that in terms of sine, because we're aiming for a substitution as a sine. And we say, okay, that would be what? Well, cosine squared, 1 minus sine squared. So 1 minus sine squared times cosine, and we're ready. What do we do? Well, we say, okay, let u equal sine, then du is cosine. And, aha, perfect, perfect. So we get this is the integral of 1 minus u squared du, which is u minus 1/3 u cubed plus c. All right, so finally we kind of got to the actual integration. Everything else was just saying rewrite, rewrite. Substitution is how can we rewrite things to look pretty. So now we're going to go back one step and say, okay, what was u? U was sine. All right, so this becomes sine theta minus 1/3 sine theta cubed plus c. Okay, but now we got to go back another step. See, there was a double substitution. That's okay. You can make more than one substitution. And so we say, okay, well, what is sine of theta? Well, we need to take a look at our triangle. And in our triangle, we say, we know that secant of theta is x, which we think of as x over 1. Secant is also hypotenuse over adjacent, which means the opposite side is the square root of x squared minus 1. And of course, no surprise, these match. So we have sine is opposite over hypotenuse. So we're going to have square root of x squared minus 1 over x minus a third times the square root of x squared minus 1 over x cubed plus c. Now, if we wanted to, we could do some various things to help us combine things together. So we're not going to, but you could. Now, of course, that I say out loud, we're not going to. It's like, I kind of want to do it now. Do I do it? Do I not do it? What are some things you could do if you really were in the mood? Well, if you really were in the mood, you could make some observations, such as the square root of x squared minus 1 cubed is another way you could express this, is square root of x squared minus 1 over x minus 1/3. And if you take a square root cube, you can combine 2 out of the 3, right? Because you have 3 square roots. You can put 2 of them together, and that would just get rid of the square root. So it'd be x squared minus 1 times the square root of x squared minus 1 all over x cubed. And then you could pull out a square root of x squared minus 1 and combine everything else together. You could do that. I don't think it gives you a lot of insight. And if anything, it starts to obfuscate the process of what you were doing. But I'm just pointing out that depending upon whom you ask, they may have an answer that looks slightly different. And that's not necessarily bad. I mean, it just means, hey, sometimes there's multiple ways to express a single answer. And that's fine. That's fine. We got to be willing to say, all right, maybe we're both right. And we just have to figure out why. Why are we both right? Well, because it's better than being both wrong. Silly Steve. All right, let's try another problem. Find the integral of t minus 5 over t squared plus 6t plus 34. And our reaction is, why is this here? This does not feel like has anything to do with trig substitution. And okay, that's a fair assessment. But I want to argue that there is a notion of trig substitution going on here. And I want to talk about what we can actually do to solve this problem. Now, if you look at your denominator, t squared plus 6t plus 34, does it factor? And you'd have to have two numbers that would multiply together to give 34, but add together to give 6. Forget it. Hopeless. Hopeless. It doesn't factor at all. So this actually has a name. So when you see a polynomial that doesn't factor, especially a quadratic, this is called an irreducible quadratic. Now, I should say, when something doesn't factor, there's a difference between it doesn't factor nicely versus it doesn't factor at all. It turns out what's true is any polynomial that we would encounter can always factor as linear terms, which means x plus or minus something, and quadratic terms, which are irreducible, x squared plus ax plus b, where it couldn't break down any further. This is an example of something that can't break down any further. So we start thinking, okay, how do we proceed on this type of problem? The way to proceed is to do the following, is to sort of say, what is trig substitution really about? I mean, when we really dig deep into it, what does it become? And if we can understand that, then progress will be made. And if we don't understand it, we're going to be scratching our heads, and the following is going to appear like magic. At the end of the day, what trig substitution is about is trying to sort of get rid of plus or minus signs in the middle. So we want to remove pluses that are in very inconvenient spots. For instance, down in the denominator. Now, square roots are where we usually try to get rid of them, but it's not the only place where we have to. And so in this case, we could say, okay, let's think about trig substitution in a way that would really clean up our denominator. So let's talk about what our denominator is. Now, in terms of trig sub, once we have our trig sub hat on, we say, oh, I need to get a varying thing squared and then a constant squared. So we look at it and say, well, the varying part, there's a t squared plus 6t, and I want that to be a square. So completing the square would say, what do we need to do? Well, we would need to, because we have a t squared, that's good. So take the middle term, divide by 2, and square it. Well, that would be 3 squared, which means 9. Now, I need to get up to 34. I have 9. How much is left? 25. Okay. So the denominator is really t plus 3 squared plus 25. Okay. Now, here's where we're going to do a slight little And our slight little is to say, t is not really how we should look at things. We should look at the world through a t plus 3 lens. So I'm going to rewrite the numerator. Okay. How? Well, instead of t minus 5, I'm going to think of it as t plus 3. And then I say, okay, what would I have to subtract to get down to t minus 5? Well, I'd have to subtract 8. And then I'm going to divide it by t plus 3 squared plus 25. And now I say, okay, I'm going to split this into 2 parts based on this minus sign. And I'm allowed to do that. I'm allowed to break addition when it's in the numerator. I'll have a t plus 3 divided by a t plus 3 squared plus 25. And I'm going to have a minus 8. I'll go ahead and pull out the constant. And then it's going to be dt divided by t plus 3 squared plus 25. And for each one of these, I can think of them individually. Now, I could even also do them collectively, but I just want to point out that individually, it's a little bit slightly different tool in terms of making it work as well as you can. So let's talk about the first one. If you look on this first integral, what's a good thing to do? Well, a good thing to do is to say, hey, what I see here is I see a t plus 3 squared, and upstairs I see a t plus 3. Well, if I take the derivative of t plus 3 squared, it would look a lot like a t plus 3. So this is set up nicely for just a normal substitution. U equals t plus 3 squared plus 25. Then we'd have our du is 2 times t plus 3 dt. Well, okay, move the 2 across. A half du is t plus 3 dt. And so what you'd end up with is the integral of 1/2, then the t plus 3 dt, du, divided by u. It's a natural log. So 1/2 natural log of u. And so the u was just the original denominator. So 1/2 natural log of t squared plus 6t plus 34. Okay, so that would be the first integral. The second integral we're going to do in a slightly different way. If you look at it, it looks like a lot like 1 over variable squared plus number. What does it feel like? It feels like arctangent. So we say, Okay, we see variable squared plus number squared. Okay, so the form is u should be our a tangent theta. So in our case, t plus 3 squared plus 5 squared, because that's 25 is 5 squared, says we should let t plus 3 equal 5 tangent theta. Or dt should equal 5 secant squared theta d theta. And now, if we simplify, well, what do we have? Minus 8. I won't forget that minus 8. Then we're going to get 5 secant squared theta d theta upstairs. And what's happening downstairs? Well, we're going to replace t plus 3 by 5 tangent theta. So it's 25 tangent squared plus 25. Well, factor out 25, then it's tangent squared plus 1, which is secant squared. And we say, wow, that's amazing. The secant squareds, cancel. And the 5 over 25, well, okay, it becomes really 1/5. So you have minus 8/5 integral d theta. Well, that's minus 8/5 theta. And now we're almost there, right? So we get minus 8/5. And then we're going to have theta. Well, solve. To divide by 5 and take arctangent. So arctangent of t plus 3 over 5. And therefore, our answer is putting these things together. So when we put these together, we end up with 1/2 log t squared plus 6t plus 34. We actually don't need an absolute value because this is strictly positive. Minus 8/5 arctangent t plus 3 over 5, and then plus c. And that's it. So in general, if you ever encounter an integral where you have an irreducible quadratic downstairs and a linear term, which just means some constant t plus some constant upstairs, this procedure will work. Complete the square downstairs. Break the numerator up as the variable in terms of, the shifted and the constant. And you say, okay, one part will become a log, one part will become an arctangent. And away you go. And you might say, well, that's great. What are the odds we'd ever see anything like that? Well, you might. And I think at least in one future session we will. So it's good to know how to handle it when we get to that point in time. Okay, good. Well, more problems, right? More problems. Let's do it. Find the surface area when the portion of the curve y equals 1 over x, where x goes from 1 to 3 to the 1/4, is spun around the x-axis. All right, well, this should be interesting. I don't know if I've actually done this before. So we're going to do this for the first time together. Wow, cool. Okay, well, let's remind ourselves about surface area. How does surface area work? So what we have this curve 1 over x. We actually know what it looks like. We're going from 1 to this very close by number, 3 to the 1/4. And we're taking just that little piece there, that little tiny segment. So this piece right here. And we're just going to spin that. And when we spin it, we're going to form a shell of something. All right, so that's what we're forming. And the question is, what's the surface area? Now, the way that surface area works is by the following. Surface area is equal to, you add up your little pieces of surface area. So we're adding up A to B. There's a 2 pi. Well, not surprising that there's a pi. Whenever we see something that's kind of circular, we should expect a pi involved. Then it's radius, length. And that's our formula for surface area. Now, in our case, we can identify our various pieces. Our A and B, well, they're given to us, 1 and 3 1/4. Okay, so 1, 3 1/4. 2 pi is 2 pi. The radius, what is that going to be? Well, in terms of the picture, it's how far we spin, because we're going around the x-axis. So this is the radius. It's from the x-axis up to the curve 1 over x. And we're going to probably write everything in terms of x. I should have said that before we started. Because we're given in terms of x, right? Our bounds are given in terms of x, so we'll stay in terms of x. So our radius, well, 1 over x. Our length, okay, what would that be? Well, the length, you might remember, that's the square root of 1 plus the derivative squared dx. All right, well, let's see what that becomes. So that would be the square root of 1 plus, now, take the derivative of 1 over x. That would be minus 1 over x squared dx. All right, well, that's it. Once we figure out how to integrate that, we'll be good to go. Of course, small subtle thing, we have to figure out how to integrate that. Okay, so let's start by cleaning things up. Well, we can do a little bit here. 1, 3 1/4, 2 pi. Now, what happens? There's a 1 over x, and this is really 1 plus 1 over x to the 4th. The minus goes away when you square it. 1 over x to the 4th. Well, let's get a common denominator. That'd be x to the 4th plus 1 over x to the 4th. Right? You can check, right? X to the 4th over x to the 4th is 1, and 1 over x to the 4th is 1 over x to the 4th. Okay, square root of x to the 4th would make it an x squared. So we got the integral at 1, 3 1/4. We have a 2 pi, and we have a square root of x to the 4th plus 1 divided by x cubed dx. Now, at this point, if it had been an x cubed upstairs, we'd be like, woohoo, x cubed upstairs, and away we go. But it wasn't upstairs. So we're not going to be going away. It's downstairs. So we got to think about it a little bit. Well, maybe we've got to think about it a lot of bit, right? So what can we do? Well, let's put on our trig substitution hat. And we say, okay, what would happen if we put on our trig substitution hat? We'd see, okay, we have this x to the 4th plus 1. Now, all right, that really says, hey, we have something like a varying part squared plus a number squared. So our kind of substitution should be a tangent substitution. U equals a tangent theta. Now, in our case, what do we have? Well, it's x squared squared plus 1 squared. So we say, okay, x squared should be tangent theta. Well, what's going to happen here? Well, we need to say that 2x dx equals secant squared theta d theta. And we say, well, do we have a 2x dx? Not quite, but maybe we can get there. What we can do is we can multiply top and bottom by x over x. Then we have a 2x dx, which is good. We like that. And then downstairs we have x to the 4th. That's actually really good for us, right? Because that would be what? That would be x squared squared, which is perfect. Beautiful. Okay, so we're on track. Okay, so let's follow this through. Now, a couple of other things. Square root of x to the 4th plus 1. Well, that'd be tangent squared plus 1, which is secant squared, and when we take the square root, it becomes secant. All right. Wow. Wonderful. This is coming together really nicely. Okay, so we have, this is equal to the integral, Okay, so there's the pi still. Haven't done anything about that. The 2x dx. The 2x dx is secant squared. So we have a secant squared d theta. We also need to leave room because we have that square root of x to the fourth plus 1, which is a secant. Okay, so that's the secant cubed. All right, good. And then what do we have? Well, downstairs we have a x to the fourth. That's x squared squared. That's a tangent squared. Okay, good. Have we accounted for everything? Let's just check. Okay, we got the 2 was involved. We got the pi, the x dx. Yep, we got that. The square root. Yep, that's a secant. And x to the fourth downstairs is tangent squared. Good. What haven't we done yet? The bounds. All right, let's do the bounds. When we plug in 1, x equals 1, tangent theta equals 1, well, that's a nice angle. That's at pi over 4. Okay, so pi fourths. Plug in 3 to the 1/4. 3 to the 1/4 squared is 3 to the 1/2, known as root 3. And whoa, tangent theta equals root 3. Oh, okay, I see what you did there. You chose some nice values. That's actually a reasonable angle. That's pi thirds. So we're going from pi over 4 to pi over 3. Great. Cool. Good job, us. Good job, us. Okay, now the only thing left to do is figure out, well, how do we actually go about integrating this thing? And I don't think there's anything immediately obvious. It doesn't look like there's a nice way to pull off a secant tangent and write everything left in terms of secant, or a nice way to pull off a secant squared and write everything else in terms of tangent. So neither of them are looking too promising right now. But I don't want to give up. So one of the things that we can always do is we can always rewrite everything in terms of sines and cosines. And a good rule of thumb is, if you're stuck on a trig integral, just put everything in terms of sines and cosines, because the nice thing about sines and cosines is we have lots of rules for them. So let's see what would happen. This would be pi over 4 to pi over 3. Then there's a pi. We have secant cubed. Now secant cubed is 1 over cosine cubed. Then we have a tangent squared downstairs. Now tangent squared is normally sine squared over cosine squared. So if we have a sine squared over cosine squared, if we turn it upside down, it becomes cosine squared over sine squared. So we're going to have a cosine squared over a sine squared. All right, so I took that tangent squared, rewrote it as sine over cosine, but of course squared, and flipped it over because I'm bringing it upstairs. All right, good. So everything so far has been accounted for, which is good. We like it when we account for everything. Now, what comes next? Well, as they say, we can certainly do a little bit of cancellation. We can cancel off, there we get a cosine squared with a cosine cubed. All right, good. So it's 1 over cosine times sine squared. Well, how do we do that? We say, okay, the good news is one of them is an odd power. Okay, in particular, we see, we have cosine to an odd power. Okay, so what can we do there? Well, this becomes equal integral pi over 4 pi over 3, and I can think of this as a single cosine. So I really got too ambitious. I shouldn't have canceled off all the cosines. And then downstairs, we could have done what? Well, it could be cosine squared times sine squared. That's 1 minus sine squared times sine squared d theta. Okay, well, we could do something there. That's making me nervous, though. It's making me a little bit too nervous. Let's step back. Maybe, can we do something back here that maybe could have helped us? Well, let's think about secant squared. Okay, I'm not saying that all hope is lost in that root. I don't want you to get like we could never succeed. We actually can. There are tools, but we may not be comfortable with them yet. We'd be left with, after a substitution of sign, we'd be left with like a du over 1 minus u squared times u squared, which can be done, but I don't know if there's a nice clean way to do it. So let's think about an alternative. So let's step back. So if we didn't put things in terms of sines and cosines, what could we do? Well, one other thing we have, there's another small idea that's worth a try. It says, secant squared is approximately tangent squared. It's like they're the same, more or less, because there's this nice identity that says tangent squared plus 1 equals secant squared. What if we did try that? What if we said, hey, let's replace this secant squared here by tangent squared plus 1? What if we did that? We could try it. And let's see what would happen. So it's certainly true that secant squared equals tangent squared plus 1. So I'm not just pulling it out of nowhere. What do we have? Well, this would be equal to integral pi over 4 to pi over 3, tangent squared over tangent squared. Okay, I'll pull the pi out in front. I don't want to lose that. Well, that would make it just a normal secant. Okay, and we can at least integrate that part. Good for us. But then we have secant over tangent squared. Okay, now what would be the integral of secant over tangent squared? Well, we'll have to think about that one. Okay. Well, let's try again. So we're going to try the same thing that we did here, except what's the difference? Well, the difference will be what? We're not going to have a secant cube. See, we had a secant cube before, now it's just secant. We were able to knock it down a little bit. So pi to the 4th, pi cubed, and then we have secant. And now the secant, that's 1 over cosine, and the tangent squared, sine squared over cosine, again, is cosine squared over sine squared. And now we're like, whoa, hey, good news. We see something that's a lot easier to work with. Okay, so this one did work. All right, cool. Well, it just goes to show. Try something. If it doesn't work, okay, try something else. And in our case, the something else that did work was, secant squared and tangent squared, they're almost the same. So they're almost interchangeable. And so we were able to do some interchanging. Now you might say, has it really helped? And the answer is yes, it's so much better. It's really a lot better. Why? Well, look, we can integrate that part, no problem. And that's just straightforward. No secrets, no surprises. And the second part, we can do it, we'll do a little bit on the side here. This would be u equals sine. Du would be cosine d theta. And what would we end up with? Well, the cosine theta d theta upstairs is our du. Sine squared downstairs is like u squared. So it's like trying to integrate 1 over u squared du, which becomes minus 1 over u. And now we're like, well, great, we can do that. Okay, so we get the following. This is equal to, well, pi, and now we integrate log secant plus tangent, okay, and then minus 1 over sine. we go. We've succeeded. We integrated. Ah, good, good. And evaluate from pi over 4 up to pi over 3. And now we just have to be patient. And when I say patient, we got to figure out what happens. All right, so plug in pi over 3. And what is secant of pi over 3? Well, cosine of pi over 3 is a half. Flip it over. Secant of pi over 3 is 2. Tangent of pi over 3 is square root of 3. So we're going to get pi, so log of 2 plus square root of 3. Okay, that's plugging pi over 3 into there. Sine of pi over 3, well, what is sine of pi over 3? Sine of pi over 3 is we're going to take square root of 3 over 2, flip it over. Okay, what does that become? Well, minus 2 over root 3. Okay, so that's pi thirds. And now subtract, plug in pi fourths. Secant of pi fourths is what? Well, root 2. Tangent of pi fourths, 1. Ah, good number. Sine of pi fourths. Well, sine of pi fourths is root 2 over 2. But you flip it over, it's 2 over root 2, also known as just root 2. And we're done. Haha. I think we don't need to simplify that. Wow, what an answer. What an amazing answer. And good. I'm glad we got an answer. Like I said, this is my first time doing it, and it's a lot of fun. All right, well, moral of this one, I suppose, is sometimes try something, and if it doesn't work, try something else. How are we going to integrate something like that? Well, stay tuned for future sessions. We'll be able to do it. We'll be able to do it soon. All right, on to more problems. Hey guys, just a quick note. I just noticed I forgot to put my minus sign here. So that should be a minus root 2. All right, easy fix, but you gotta pay attention. Okay, back to work. Okay, on to our next problem. Find the length of the curve y equals a half x squared between 0 less than or equal to x less than or equal to 2. And then there's sort of a side note here. Oh, well, I think we know where we're going when we have that little side note, but let's take a look at it. Now, a half x squared, lovely curve, right? Parabola, almost as good as you can get if you're not a straight line. So you think, oh, well, it should be an easy integral to do, right? So what's the length? So the formula for length is add up a to b square root 1 plus dy dx squared dx. That's the formula. Okay, well, we know a and b, 0 and 2. So add up from 0 to 2, square root of 1 plus, and take the derivative, square root of a half x squared is x, square that, x squared. And now we're like, wow, okay. Now, square root of 1 minus x squared, we actually can do that even if we didn't have trig substitution, when it's a definite integral, because we can do circles. Square root of 1 plus x squared, how much harder could it be? Well, what do we see? It's of the form a squared plus u squared, and when we see that form, we say, okay, that should be something a tangent theta. So in our case, 1 squared plus x squared. Okay, so x should be tangent theta. That means dx is secant squared theta d theta, and the square root of 1 plus x squared. Well, that's the square root of 1 plus tangent squared, which is square root of secant squared, which is secant. So what do we get? Okay, we get, this is the integral, square root of 1 plus x squared, secant dx, secant squared. So we have secant theta times secant squared theta d theta. Now, we can actually talk about our bounds. What do we have? Well, when we have the lower bound of 0, that corresponds to x equals 0. When x equals 0, well, for what angle does tangent of theta give us 0? Then the answer is 0. So we still have 0. Now the upper bound, that's a little bit more interesting. So that's x equals 2. So now we have 2 equals tangent theta. So solving for theta, theta would be arctangent of 2. All right, great. So that's what we have to solve. Well, let's think about it. We have to integrate secant cubed. Now, if you remember our trigonometric integrals, there's a basic rule of thumb that says, hey, tangents and secants, they're not so bad unless you have secant to an odd power. And then a long journey lies ahead. This is secant cubed. That's secant to an odd power. But they were very nice to us. And they made us a note. That's the integral. Because here the point is the actual substitution, the trig substitution part. We don't want to get too bogged down by, all right, now let's spend the next 20 minutes integrating secant cubed. So, okay, great. This is 1/2 secant theta tangent theta plus 1/2 natural log of secant theta plus tangent theta. And evaluate 0 to arctan of 2. Now, if you look, when you plug in 0, tangent of 0, 0. That means that's a 0 as well. Secant of 0 is 1, log of 1 is 0. Okay, phew. So we only need to plug in arctangent of 2. Now, to help us do that, let's draw ourselves a picture. Suppose we have the angle arctangent of 2, because the output of the arctangent will be an angle. So that's saying, look, we're really interested, when does tangent equal 2? So that would be, if you think about our triangle, opposite over adjacent, and then hypotenuse would be the square root of 5. So let's go through it. We have secant of arctangent of 2. Okay, that's like secant of alpha. And secant is hypotenuse over adjacent. So we have 1/2 times square root of 5 times tangent of arctangent of 2, which is 2, plus 1/2 log, and now secant, still hypotenuse over adjacent, square root of 5, and tangent, still 2. Well, the 1/2 and the 2 cancel, so we end up with square root of 5 plus 1/2 natural log. Well, I'll write it as 2 plus square root of 5. And that's it. Now, sort of the punchline to this is the idea says, look, even a very simple curve, because of the introduction of the square root, leads to kind of a tricky integral. And on the other hand, we saw, well, we came up with these really complicated looking curves, and they led to very simple integrals. So there's always a trade-off. You have to pay a price at some time when you talk about arc length. Either you have to have a very complicated function at the start so that you get a simple integral later on, or you can have a simple function at the start, but you'll get a complicated integral. But in the end, we have the tools, and we can make progress on a lot of these problems. All right, good. Well, I think we have time for one more problem to help us finish up on a nice, relaxing, gentle cool down. Find the integral of du divided by square root of u square root of u minus 6, and u minus 3 cubed. Wow. Okay. Oh, wow. All right. This should be interesting. Now, you look at it, and maybe it's not so clear. Okay, what's the right tool here? Now, we know the mindset for today. We're like, hey, we're practicing trig substitution here. But what are some things that are suggesting trig substitution? It's certainly not the u minus 3 cubed. That's not suggesting trig substitution. The square root of u minus 6 by itself also is not a suggestion of trig substitution because there's not really a square on the inside. But we say, look, there's another square root. So what we can do is we can talk about combining. So this is the square root of u squared minus 6u. Now that feels a lot more along the lines of what we would think of when we think of trig substitution. But we're not there yet, right? Because when we want to do trig substitution, we want to have like something varying squared and a constant squared. And that's not what we have yet. But we kind of see where we're going. We say, okay, well, what we'll do is we'll think of this as square root u squared minus 6u. And then we say, what do we need to do to get a square here? So we want our varying part to be a square. We want to complete the square. The good news is, of course, what's in front of the u squared is 1. So completing the square, you'd add 9. Well, we'd also need to subtract 9. So we say, aha, we really have the square root of u minus 3 squared minus 3 squared. And now we're actually feeling pretty good because it does feel more like a trig substitution problem. Variable squared minus a constant squared, okay. It also, see the u minus 3 lines up, almost as if it had been planned to happen, because I think it was planned to happen. All right, well, let's figure out what our pieces are going to become. So this is of the form variable squared minus number squared. And when we see that, the right substitution to make is to make the substitution u equals a secant theta. We're already using u's. Okay, well, I'll make w's, right? If you're already using u, go twice as far, w. So w should be a secant theta. So in our case, where we have u minus 3 squared minus 3 squared, well, look, that says u minus 3 should be 3 secant theta. Okay, now we have our setup. Taking the derivative, du, derivative of secant is secant tangent. And of course, this expression, the square root of u minus 3 squared minus 3 squared, well, okay, that becomes 3 secant, all that squared, minus 3 squared. That's pulling out the 3. All right, pull the 3 out. Then we have secant squared minus 1, which is tangent squared. Take the square root, is tangent. All right, great. So what does this become? We have the following. This equals the first part, this piece here, that's this square root term. So that will become 3 tangent theta. The u minus 3 cubed will be 3 secant cubed. The du is going to become 3 secant theta tangent theta d theta. Whoops, I forgot to put d theta there. I keep forgetting that. Good to get into the habit. Good notation always pays off in the long run. So let's be careful here and see what we can do. We can clean up a little bit. Certainly we can say, look, we can get a tangent to cancel, that's good. Get a 3 to cancel, that's great. What do we have? Well, we have a 3 cubed, So that will give us a 1 over 27. So we want to pull that out. And then we have a secant, and there's a secant cubed. Okay, so secant over secant cubed makes a secant squared. Well, secant squared, how do we integrate that? That is, flip it over. So that would become cosine squared. All right, well, for that, power reduction. So 1 over 54, because remember, power reduction, cosine squared would be a half. So a half times 1 over 27 is 54th. And then we'd have the integral of 1 plus cosine 2 theta. Okay, so we get 1 over 54, and now theta, and then the integral of cosine 2 theta would be sine of 2 theta, but we need to multiply by a factor of a half. That factor of a half because of the 2. All right, good. So we've integrated. Aha! But we're not done. We got to work our way back. And so to start working our way back, we say, well, we need to clean up. That sine of 2 theta, not quite the right form. We really want to get everything in terms of like sine theta, cosine theta. But we can say, look, a half sine 2 theta is really sine theta times cosine theta. So, all right, that's good. So we almost have all our pieces in play. What do we say? Well, we can see secant of theta would be u minus 3 over 3. So I'm just starting with the relationship. And so, in terms of our triangle, we have our angle. Secant is the hypotenuse over the adjacent side. This missing side, well, that'll be the square root of u minus 3 squared minus 3 squared, which is the square root of u squared minus 6u. See, this square root of u squared minus 6u, that's really where we had our starting point for doing trig substitution. So, where do we end up? Well, we end up with the following. We have a 1 over 54. So theta is an arcsecant. So we have arcsecant of u minus 3 over 3. Now, I will say some automatic computer solvers don't like arcsecant, so they express it in different ways. So, for example, sometimes you'll see like arctangent of the square root of u squared minus 6u over 3. That works too, but I like to go based off of our substitution. Okay, and now that's that term, and then say, okay, plus sine of theta times cosine theta. Well, sine of theta would be opposite over hypotenuse. Cosine of theta would be adjacent over hypotenuse. So when we multiply them together, we're going to have in the numerator the opposite and the adjacent side multiplied together. So 3 square root u squared minus 6u. And then in the denominator, we'd have this hypotenuse squared, u minus 3 squared. And, of course, a plus c, and we're done. Everything's back where we started. Good. Well, a nice little cool down problem at the end. We did a lot of practice. It's important to keep doing it. The more you practice, the better you get. And the more natural it will feel. A lot of times the people who struggle with trig substitution struggle because it doesn't feel natural. And so they're sort of fighting with it. But once you practice, you're like, oh, I don't have to fight with you. We can actually get along pretty well. Let's become friends. And we're like, yeah, good. That's a great way to approach it. Be friendly with your calculus problems. Well, thank you for coming. I really do appreciate you sticking to the end. I hope you have a great day. Bye.